talk tonight is John DeRoot, who's going to give us a talk on a proposal for a generic transaction engine. So, John, come on up. So you did the lapel mic. You know how that works, right? So this is the microphone. You can test it.
Oh, yep. Okay, that works. Come on. Come with us, you know. All right. No, so I don't have my comments. That's good. Okay, so I'm going to kick us off by talking about a riveting, absolutely riveting topic. We're going to talk about a common transactional API for HBase. It's out there in the form of a JIRA 11447. And yeah, so it's just the space bar, that's right. Okay, first off, I wanted to acknowledge some people. You know, this sort of thing isn't possible to do on your own, really, and we've had some really great input from folks from a number of companies and also from outside, and particularly people within HG as well. So there's been a great response. So thank you everyone who's contributed. I know you're all out there. So what are we aiming at with this thing? Really, we're trying to produce a simple API that will give us, I don't have my notes here, but that'll provide transactional support, fully support transactions, and yeah, it needs to be a single consistent transaction interface. So we want it to be the same across different transaction managers, and that's very important for us. We also wanted to make the transaction manager choice parameterizable so that you can select the transaction manager at runtime, configure it, and not change your code. That was one thing we really wanted, so the customers could just write their code once, and then they can select a transaction manager that really works for them. Okay, I think I've talked over some of the next slide. Okay, so overall, the aim for doing this, the motivation behind it, was to accelerate the adoption of transactions within the HBase community. And we know that transactions are starting to become, people are starting to get interested in them. We have a number of transaction managers out there now, both open source and closed and proprietary. But we wanted to make it easier for people to use transactions and maybe try and get some confidence behind it. What we're not going to cover in this API, sorry. Sorry, I'm on the wrong slide, aren't I? Okay, so why are we doing it now? Sorry, covered that already. Okay, well, we're using different interfaces. And the other point that really I forgot to make there was that we're seeing HBase being used in new ways. For example, in OLTP, which is an area where transactions would be very important. So, this is supposed to be summarizing the basics of the API. You notice I still haven't got into any specifics at all. We want it to be independent. The API should be independent of the transaction manager. That was one of the key features, that you'd be able to use it and not worry about which transaction manager you were coding to. It needs to be simple and as much as possible similar to the existing transactional APIs that people already have implemented out there on HBase. And the rationale behind that was to make it easy to fit into the existing models that are there. And of course, we wanted to be able to switch transaction managers through properties. Another point, and this is one that Gary just mentioned before, it needs to be extensible too. We want to be able to allow transaction managers to deliver new features unique to themselves on top of the API, so that they can add value and they can expose things which are unique to their own design. What we're not doing here is two-phase commit. Okay, so if you think about transaction management, you usually think about two-phase commit, right? Well, that's really an implementation detail. As far as the application is concerned, all it really needs to do is begin a transaction and then decide what it's going to do with it. Whether it's going to commit it or roll it back. It doesn't need to worry about the two-phase commit. That's done underneath, unless you're doing heterogeneous two-phase commit or heterogeneous transactions. Things like XA and JTA use a two-phase protocol, but we're not intending to implement those in the first cut. We'll probably get there one day if we're successful. We're not doing TDL support, so there's no support for transactional table creates, table drops, that sort of thing. Yeah, that's another point. We also felt that it was important to only have one transaction manager running at a time. If you've got an HBase instance accessing data, you don't want two transaction managers competing for that data. Right? So you make that choice when you start HBase, and it would be one transaction manager, and if you wanted to change it, you could bring HBase down and bring it back up with a new set of properties. The other thing that isn't supported here is we're not tying tables to transactions. So you can do work which is both transactional and non-transactional against the same tables. And of course the caveat there is that if you do it, and if you're doing it at the same time, then you're obviously compromising your own integrity. The data integrity, so don't do it. Okay, so there's three classes. It's a very simple interface. There's a transaction service, which really represents a transaction manager. There's a transaction object or class, which represents the transaction. And then we have a transaction table, which is really just HTable with a little bit of extension. Now I'm going to go through those in a little more detail. The transaction service class, it's, as I said, there's really only one of these. You instantiate one when you start the program, and it provides you with services which are transaction manager related. Things like when you want to globally set an isolation level, or you want, that sort of thing, set a transaction timeout at a global level. So it's those sorts of things you use. And notice it takes a configuration parameter so that it can be configured through the HBase site.xml file. The transaction class is really the core of this thing. And so your transaction object, when you instantiate a transaction object, you're beginning a transaction or you're adding a participant to a transaction. And so you can think of, if any of you worked with transactions before, you know what begin transaction or begin work in SQL is. And so when you instantiate this class, this object, you are beginning a transaction, right? And obviously you have to be able to commit it or roll it back. And now that representation, typically you would use transactions, we envisage this to be at a thread level. I'm not going to really talk about threads today too much, but I think most of you are probably aware that HTable is not thread safe, right? And so typically you have separate instances of your HTable, different threads. Well, with transactions, you probably keep them to a single thread. You probably create a transaction instance for a thread. That's the way I would see it. working most seamlessly. There's another method here. Wasn't really intending to talk much about it, but you can also stream the transaction into a byte array and then use that as a portable form. Because one of the things that we wanted to be able to do was to allow a transaction to have multiple participants at the same time. So several threads, several processes, all running against the same transaction, doing work at the same time. So that's what that last one, 2 byte arrays, was about. And there's a constructor in there also, a second constructor shown. It's for the same purpose. And the last one, probably the most contentious, is the transaction table. It's derived from HTable. It's there's only one change from HTable, and that is that we've added a set transaction method to it. And set transaction just lets you associate the transaction object with the table, so that you can then go and do your work against it. We'll see that in the next slide. You can do some work against that table within the transaction, and then you can decide whether you're going to commit or roll it back or whatever you're going to do. Okay. So this is our sample code here. Things I really want to highlight in this are, if you look at the third line down, we've got here. So 1, 2, 3. Yeah, third line down. We're in. Third line down there. It's hard from here. We're instantiating transaction service object, and then we create a new transaction. This is a very basic application. Obviously, it's missing some stuff, but it's trying to convey how it would really work. So it creates a table reference, and then it's setting a transaction here. Right, so it's setting the transaction for that table. It does some work, so a couple of puts against the table, and then it decides to commit. Okay. Now, what we've done with the tables at the moment in the spec or the proposal is that a transaction table is only used transactionally. And that's not. I know I said before that you could mix transactions and non-transactional work. Well, you can do it, but not using transaction table. If you use transaction table, then that has to be transactional, and it'll throw an exception if you don't have a transaction when you do a put, for example.
John, do you have a question?
Yes.
Do you want to?
Would you like Mike?
So it's a quick question. So is that set transaction method so that you can have transactions across multiple tables?
Yes. Okay. But the set is, this is for a table, right? That's for a specific table. You could do this. You could have another table which you also set the transaction, same transaction on, and then you could perform work across multiple tables against the same transaction. And you can also do it in multiple threads, right?
So I have a question for you. So once I've done the set transaction, is there a way to disassociate the transaction with the table before I do the commit, or must I do the
Not at the moment, no. No, there's not. There's a way of streaming the transaction into something portable, but that's not changing the transaction context against the table. So the way I sort of looked at it really with this is that you would use your table. You can reuse the table after the transaction completes, right, by performing another set. But there's no sort of set it to empty.
Okay, so after I do a tx1.commit, or I assume there's an abort or rollback, then I would have to create a new transaction object and associate that, right?
That's right. Yeah. But you could set it to another transaction.
So,
Sorry.
Okay, so before we call the tx1.commit, if I call txtable.flush, what do we have?
Microphone.
Sorry. You try again.
Oh, I'm asking, my question is, before the transaction that commit, if we call TX transaction table that flush, what will happen?
It will flush it to disk, right? It will flush. Flush is not really part of the transaction.
So it will flush it to the table, so the data will get into the HBase.
I think we'll have to, that's probably going to be something we'll have to override on a transaction manager basis. So we may have to.
Flush could mean that the data is sent to server, but it still would not finish the transaction.
Yeah, you can't finish the transaction until commit, because most of these transaction manager implementations use MVCC, multiple version concurrency control, and so they can't actually completely transact. They can't flush anything until they get to the commit phase.
I see. So are you saying the MVCC is in the client side, in the transaction side?
It's in the transaction manager.
Okay.
So that's hidden under the implementation.
Yeah. Okay, thank you.
But you're right, the things like flush, there are things that would need to be overridden, but the idea was that the API itself would be consistent.
Right. So, assuming that set transaction method is equivalent to begin transaction, right?
Yeah.
And if I have multiple...
So set transaction is not actually equivalent to begin. Creating the transaction object.
Okay. So, for example, if I have a multiple participant table in a single transaction, this set transaction has to be called on each of those tables before you can do any kind of mutation on that?
Yes, that's correct.
Transaction.
Yes.
So, would the API provide some sort of synchronization method where it ensures, okay, everyone knows that they have called set transaction, or the consumer has to manage that rendezvous?
Right now, let's look at that.
Because you're talking about multiple threads, and then doing a multi-table, multi-thread transaction on a single transaction object could become
It could become funny, yeah. And in fact, can you talk for a second? It does raise a point too that this is a fluid spec. We started this only maybe a month ago or less, and so we're looking for your input into this.
I think it is important to set define the guarantees that we are going to make, which are practical and easy to use as well.
Yes, okay, excellent. So could you go to the Jira and add some comments? Excellent. Thank you. And in fact, before we get to more questions, I just want to go to the next slide, which is the last one, which is my plug for you to all go and look at the proposal online. It's easy to find. All you have to do is just Google Jira HBase 1144.7, and it'll come right up at the top of the search. The current proposal out there is 0.5. I'm working on 0.6 now, and I know that there's a few people in the room who have input into that, and it'll evolve. It's going to evolve quite a bit. You can also, on the Jira, of course, find the entire discussion history. So you can look at what other people have said and what sort of rationale you can come up with for it. We're hoping to put up, we have a sample application we're going to put up there. But of course, that's going to change too with time. And we are talking about putting together a compatibility scheme to go into HBase to make it consistent. So that was it. Please add your comments to the Jira.
So does the sample code include a sample transaction manager?
No, not yet, but it will do. Sorry. So that's my plug. So questions? Any other questions?
Do you have a question here?
Just turned it off.
Could you please go to the...
Oh, sorry. I just turned it off instead of on.
No, muting now. Yes, okay.
Can you hear me now? Good. If you would go back to the previous slide,
Yes.
wondering what will happen if there's another thread, right, doing a read between the two probes, right? If the read in this case will be 01 in another thread, where that thread, if the read the data that is being put into TX table?
Yeah, that is a good question actually, and that is a typical transaction management thing. Yeah, under well, at least the one that I'm familiar with, MVC, the multi-version concurrency control. What it does, it actually retains a list, called the right list or right ordering list, of all the operations that have occurred, the right operations that have occurred in the transaction. So the puts are listed in there. And it references that table before it goes to disk. So when you do a get, it's going to I think I'm talking about the right thing, am I? Yeah, good. So when you do a get, it's going to look in that table to see whether the value's there before it goes to disk to check there. There are other implementations I know that Community, Gary is going to talk soon. They use a timestamp system, which is probably more like a snapshot isolation, I'm guessing. So, but yeah, there's always a way of doing that. You need to, it's a very important part of the concurrency.
No, thank you.
Okay.
Lorenzo?
So would that API
You have to eat the microphone.
Okay. Would that API
Oh, wait.
Must be on.
Hello? So would this API also take care of some kind of, suppose this code is running in a server which is taking care of multiple transactions, and then there are multiple independent transactions working on the same table.
Yes.
And there is a need of locking and all of those things.
Yep. Yeah, that's it. That's actually a transaction manager function. So typically, well, we see it that way anyway. Most of the transaction managers will provide you with either a lock manager semantic or an NPCC type semantic snapshot isolation, something that will give you that protection. Yes.
So that is outside the scope of this API, and that is like
You just assume that works. Right, when you write this code, you're assuming that works. And in fact, you can actually set, you notice we talked earlier about isolation levels. You can set the different isolation levels. And depending on what the TM, the transaction manager you're using, supports, you can set that isolation level at whatever serializability level you want. Okay.
So there could be an instance where another thread in the same program does not want to read the modified value until the transaction is committed. So I still want to work on the older value. So I will open a new transaction table and that will give me the older value.
Well, I can tell you that ours will definitely give you the older value, and that there's no other option at the moment. And again, it would depend on the implementation and the level of isolation you have. So, yes. It's not working. I don't know what's wrong with it. Hit it. Yeah. That sounds good. Yeah.
So I think it's related to the previous question. But one point, which point is the locking happening on the table? Especially in the context of read modify write. Because if we have several threads, we have to have some security, and let's say just something like atomic interval.
Yes.
Since the person will have to lock because it just begins the transaction. So
No, you're not really. That depends again on the isolation level you select, when the lock is applied. So, and most of the implementations out there that I've seen anyway, the transaction managers on HBase are not actually using the locking semantic. They use this concurrency control mechanism, which has no locking at all. Actually, it really just, you can think of it as taking a snapshot of the data. So it says, okay, the data looks like this at this point, and that's what you're going to see in this transaction. But that's not true in all of them either.
The issue, for example, with canceling is that just think about quantities, for example. So if you are like a seller, sells a merchant, right, and you have to manage your quantity. So having this method is not good enough because once there's already introduction to newspaper, the server of Fed actually seeing the same quantity and have snapshots and they all try to reduce the quantity at the same time, even if it will kind of serialize, you're still going to get the wrong.
You can use the wrong value.
You're going to actually sell negative quantity.
That's right. So that's where you need to be able to have multiple isolation levels to get the right one for your application.
How is the isolation level going to be managed? Is it going to be automatic through the transaction manager?
Yes, and in fact, which levels are available will be up to the transaction manager. Sorry, you get it? Yes.
Well, actually, I have two questions related. The first question is, are the isolation levels provided or defined as part of the API? The second question is, I see you have a TX1.commit.
Yeah.
The commit attempt would return the result because that commit could fail if there was another completed transaction.
Yeah, and that's something I didn't go into. That's true.
How does this code or the application that uses this API, how does it get notified of an abort or a transaction or a deadlock?
Okay, so I'll answer the question on isolation levels first. We've defined isolation levels in the specification or the pro proposal, all right? And in fact, there is an API method that will return you which isolation levels this transaction manager supports. Okay? And the second question, and I haven't talked about that in all here. In fact, it's driven through exception handling.
Okay.
Okay, so it'll throw an exception if it does.
Okay, so the commit fails if you throw an exception.
Yes, and in fact those exceptions are also defined in the proposal.
How about deadlocks?
There are no deadlocks with MVCC, so deadlock handling would definitely be a problem in a lock manager. It's something we would need to handle, or the transaction manager implementation would need to handle. Yep, thank you. Okay, because we want to give Gary some time too. Yeah. All right. Hand it over. So thank you, everyone.
The other mic died, so I guess we'll share this one. See next. I think Gary wanted to say something from continuity. Where are you, Gary? So are you going to make a presentation? So you have a Mac, right? I see a Mac. Do you have an adapter? You do have an adapter. Good. Hang on, let me disconnect here.
So, hi everybody. Can you all hear me? So I work for a company called Continuity, and I'm here to talk about a project we have called Continuity Tephra. Now, first, a little note about who we are. I'm an HBase committer. I've been working on HBase for 4 or 5 years now. I work for a company called Continuity, which provides a product called Continuity Reactor. And that you can think of as a scale-out application server for you. It makes it easy to build a distributed application. So we're really focused on making the developer's life easier, making it easier to deploy, manage applications that are built on Hadoop HBase. We also have a great team that has a lot of experience working with and contributing to open source, and we plan to continue doing that. So we're going to keep this short because we actually talked about our transaction implementation at an HBase meetup a few months ago, so I'm not going to go into a lot of detail. But I'm here to talk about a project called Tephra, which is our transactions implementation from Reactor. So Tephra is a distributed, scalable transaction engine that we built that works on top of Apache HBase and Hadoop. It has a few key components. There's a central transaction manager that issues time-based, globally unique transaction IDs that are used for writes. And it also performs conflict detection. Now, our system leverages a number of key HBase features in order to work, and so in order to perform well. So, as John was mentioning, we override the HBase timestamp in order to isolate writes from individual transactions. So this gives us basically a multi-version concurrency control that provides each snapshot, each transaction with its own snapshot of the data that exists, and that provides snapshot isolation for concurrent transactions. And we also utilize server-side filters to efficiently read data transactionally. So push down filtering to the server side, filter out data from transactions that failed or from in-progress transactions. And we also use HBase coprocessors in order to clean up data from transactions that have failed and could not be rolled back for whatever reason. Say the client failed and couldn't complete any rollback process, as well as data from no longer visible transactions. So new versions have been written. Here. If new versions have been written that now hide and mask previous values. Another key design goal of Tephra is, well, we love HBase and it's really a core part of our platform that we built on top of. We want to keep our engine extensible so that it can be integrated with other systems as well. So we also have the ability to do transactional reads from files in HDFS, for example. And we want to keep things open so that it can be extended to other systems, say relational databases. So, big announcement that I'm here to make is that we're open sourcing Tephra under an Apache 2.0 license. Why are we doing this? Well, we think that HBase is great. We use it heavily. We've worked with it for a long time, but it still leaves a lot of problems difficult to solve. Say you want to create secondary indexes on HBase. That requires that generally you write to 2 separate tables. You have to keep those writes coordinated somehow. Now, how you actually keep those consistent is up to you, because unfortunately HBase only, very reasonably so, but only supports atomic operations within a single region. So we believe that Tephra makes HBase better, makes application developers' lives easier, and makes a lot of these problems easier to solve. So by performing writes to your secondary index within the same transaction, you can easily make those writes globally visible at once. They're atomic. And if the right to either table fails, the rights can be rolled back together. We also view this as a great opportunity to contribute back to the HBase community that we've been able and lucky to build a business on. And as open source, we really want to see how other people make use of this and see how the project can grow. So with that, I'm going to take you to our GitHub page for Tephra. Currently private, but stay with me. I hope I remember this. All right. So Tephra is now public. So with that, please go to our GitHub page and check it out. Download it. We have documentation on how to get started with it, what the client APIs look like. I'm not going to go into a lot of detail about that here, but now that this is open source, it should make it a little bit easier for us to illustrate some of the design choices we've made and the APIs we use and contribute to the discussion around building a common transaction API for HBase. We also have a Google group set up for development and user discussions. And the previous presentation that I alluded to is also available on SlideShare. If you want to see a lot more detail about how it works, go and check that out. It's kind of exhausting in detail. So, with that, does anyone have any questions? Yes.
The previous presentation was about the generic transaction management for HBase.
Yes.
Is it going to be any revision to it though?
So we've been making comments on the proposed API for HBase. I think now that our implementation is open source, it'll be a lot easier to illustrate the client APIs that we currently present. So I think the challenge with providing a common transaction API for HBase is, as John mentioned, there are a number of different implementations out there that all make different design choices, that are implemented different ways. And so the challenge is finding the commonality between those. To find the commonality between those, you have to be able to see what they all look like. Right? So I think by illustrating the client API and design choices we've made, we'll be able to have a more informed discussion from some of the things that have motivated our decisions.
Maybe some of the questions. What's the level of maturity of the Tephra right now?
So it's been a core part of our core product for over a year now, and we have customers using it in production. So it's been heavily used and tested. I mean, obviously it's a new open source project, so I'm sure as you add more eyes to it, people will have different ideas and different thoughts of things that they want to see from it, so I'm sure it'll continue to evolve. Okay. Yes.
Any numbers on the performance overhead of multi-row transactions? Or like, if you have any comparison that you can share?
So the writes that are performed as part of our transactions are normal HBase writes. We override the timestamps. So the overhead amounts to a separate RPC call to start the transaction, separate RPC call to commit the transaction. And it's really a matter of how high that overhead is, depends on how many operations you're performing within that transaction over which it can be amortized. So one option for mitigating the overhead is to do batching of multiple operations together. And so from the testing that we've seen, our transaction service has never been bottlenecked in the testing that we've done in HBase. So I can't give exact percentage overheads because it's going to vary by workload and by the types of transactions you're doing.
So you mentioned that it overrides the timestamp of the cells, which means the user does lose the ability to specify their own, which is a good thing.
So the user loses the ability to exactly specify their own timestamp. That's correct. But our transaction IDs are time-based, so you can still do things like set TTL on column families. All that's still possible. You can still derive the wall clock time of the transaction ID. Yes. Good.
Are you going to make it a Apache project?
So I think the plan at the moment is to have it open, see how it evolves, and if it makes sense, propose it for incubation in Apache. But I think that's a high hurdle to jump to immediately for a new project. So I think it makes sense to give it a little bit of breathing room on Git and see, and hopefully develop some community around it first and let that drive really pushing it into Apache. Yes?
You just mentioned use the core processor to implement the rollback, right?
So the coprocessors do a couple of things. They inject server-side filters for reads, so that the client doesn't have to consistently do that from their end. They also, so if the client fails to roll back all the writes that were part of a transaction, the transaction is marked as invalid. So the coprocessor has a view of which transactions are invalid. And we hook into flush and compaction operations on the server side. So as we're going through the cells during a flush or compaction, if those cells match transaction ID from an invalid transaction, we'll drop them so that data does not accumulate over time. So even in the case, say, the client fails and one of the writes that were flushed out could actually be rolled back, it'll still be cleaned up later during flush or compaction.
What is the isolation level available?
So all we support is snapshot isolation.
So architecture-wise, is this a centralized transaction manager or is it distributed?
There is a centralized transaction manager that has a global view of the in-progress transaction state. So we provide for automatic failover of that transaction manager. You can run multiple of them and perform leader election amongst themselves if one of them fails. Any other running instance says race to take over that leader role. There's a service discovery mechanism, so all that's transparent from the client side. But there is a single centralized process. And that's necessary currently in order to efficiently do conflict detection. So all that's able to be performed quickly by doing in-memory lookups.
So in our use case, that centralized transaction manager never could be a bottleneck?
So, I mean, we do anticipate that at some point in the future, we want to scale beyond a single transaction manager. Obviously, that brings complexity. It means that you need to look at partitioning your transactions in a way that makes sense for the application so that you're not crossing those boundaries across multiple managers. When you do cross those boundaries across multiple managers, you'll either need to do something like do a base commit or a consensus protocol across them. So that's not a level of complexity we've tackled yet. It is something we expect we'll get to. It just hasn't been found to be the performance bottleneck so far for any of our cases. All right, thanks everyone. I'll hand it over to the next presenter.
So next up we have Neil and Archie from Optimizely. And they have a Mac, so they can use your adapter.
This one's got HDMI.
Oh, it does, okay, so you're good. You're gonna have to share a mic. So how do you want to do this?
We're just gonna take. Yeah, we're just gonna switch midway, so I'll just hand this over to Harpreet. Hello everyone, I'm actually Mustafa. Neil couldn't make it, so I'm stepping in his place. And I work at Optimizely, and today I want to tell you about transactions. Not really. I want to tell you about unique counting with very high volume ingest. Alright. Well, first of all, what's Optimizely? Well, we do A/B testing. That means we let our customers run randomized tests on their websites, which means we let them serve different experiences to different customer subsets and measure the outcomes of those experiences. My team handles the measurement part. We have some really smart people who work on the experience serving, but I'm not one of them. So this is our results page. You can see you get the people in the experiment, how long the experiment's been running, how many variations there are, so on and so forth. And I first want to tell you just a little bit about what makes an experiment. Well, first you need some variations. This is sort of like the different experiences. Like this could be different colors of your like buy now button or like a different title text, right? And then you've got one or more goals. So these are things you want your customers to do. Buy something or like go to this page, which means they've registered, so on and so forth, right? So what we want to do with these experiments is we want to measure the impact of different variations on different goals. Well, what does that mean? Well, that means changing conversion rates. And we define conversion rate as the unique number of conversions divided by the unique users who visited a particular page over time. And then we sprinkle some statistics, fairy dust on it, and then we get a chance to beat baseline, right? So this tells you this variation has improved this particular goal, right? So what do we mean by unique counting? And this means, this is very similar to, like monthly active users or daily active users. It's basically unified on user ID. So if you think in SQL terms, it's a select distinct user ID from whatever, right? And in our case, each experiment has its own unique horizon. So when we do a unique count, it means unique for how long that experiment's been running, and each experiment has a different timeline, which means we need a different counter for each experiment, right? And unique counters are actually pretty hard because you can either just keep everything in memory. You have like a giant hash table, and you check the hash table, and if you haven't seen something, increment the counter and make sure you don't have any race conditions around that. And you also have to keep everything in memory if you're doing this, right? This kind of sucks. Or you just sort by your unique key, in which case you can do like an all-event scan on the data and get a correct unique count. But if you're actually sort of like trying to keep everything in order, or you're just trying to like insert into the middle of things and you're jumping around, you're trying to do a lot of inserts, this can be a problem too. And I actually lied. There's a third option, which is to do approximate counting, and this is what most people do. They use things like hyperlog. This is awesome. If you can do this instead. Don't do what you're doing. But our customers, because they're trying to measure improvements in conversion rate and because they're changing things on their page, they really hate approximate counts. So we're stuck with exact counts. So here's how we did that. Okay, so now we're back to the first two options. How do we pick which one to go with? Well, we had a very high write load. We actually, when we submitted this talk, we were at 3 billion puts. We just broke it 4 last week, so a lot of puts. On the read load, though, we only get 200K API requests. I mean, those are requests with aggregate requested by the results page that I showed you earlier a day. That's a much smaller number than the write load, right? So that tells you if the reads are pretty expensive, we can live with that. you can't live with the expensive writes, but if you need to do a linear scan or experiment data to serve results to a user, we can probably deal with that. So why don't we stick with the second option, which is sorting by the unique key. In this case, user ID, right? So, and HBase is perfect for this. Like, if you have a single critical query and you need to make it fast, you just pick your row key based on that query. You know what ours is. If we had like 5 different queries, we'd need 5 different tables. That wouldn't be the end of the world, but since we have a very focused query, this is good. HBase also does log structured merge trees, which is a fancy way of saying, when you write to HBase, you append to the write-ahead log, and then you just like drop something into like mem store. You're not like hitting this, right? And then that mem store is a bulk flash that happens however often you want it to happen, which means that at our ingest rate, HBase really sings. And then finally, for the kind of linear scan that I was talking about, you can use coprocessors to do the scan and just return the aggregates. You don't have to send all the like event metadata tags, whatever stuff you don't care about, over the wire. You can just return the totals, right? So HBase is great. Now that I've told you about why we chose HBase and what we do, Harpreet is going to tell you about how we use it and how we sort of tune it over time to get it to work at our scale.
So my name is Harpreet, and I'm going to dig a bit deeper into the overall architecture of how we're building this new system on top of HBase. So as you can see here, we're actually using Flume for real-time ingest. Flume is a dynamically defined data pipeline with multiple sinks, and we use it basically to batch up our writes, which go to HBase and to S3. And Flume has this capability to just take your events and just channel them to different channels and put them into different sinks. So other than the real-time ingest, we also have the ability to bulk load a lot of data, and we mostly do that for either migrating data from our old system, or if we ever want to restore data from our archives. And the way to do that is to create some H files from MapReduce job and simply load that using the complete workload tool from HBase. And always remember to pre-split your table. So for the read requests, we actually fire a coprocessor run for each request that we get. And the coprocessor simply just scans through all the rows that correspond to a particular experiment. And as Mustafa already mentioned, we have those rows ordered by the user ID, so we can easily do unique counts over that. So I'm going to talk a bit about schema, because that's definitely one of the most important things to decide whenever you're creating a new system onto HBase. And when we started off, we picked this fairly simple design where we just put experiment ID, variation ID, and the user ID into the row key, and the goals were the columns. And we use the event timestamp as the HBase timestamp, and that really helps us make sure that all our writes are idempotent, which is really important in this kind of system. So one thing that we found with this schema is that our row keys are really large. And with HBase, row keys get stored along with each cell. And that means that if you have really large row keys, then you're wasting a lot of storage, and it can have a big impact on your performance even when you're doing scans. So one thing that we really recommend for anyone is if there's anything that you can take out from your row keys, always do that. And in our case, we found that we could just take out variation ID, because whenever we were doing any kind of scans, we only cared about like getting the whole experiment, so we might as well just put it into the column. The other thing we found was that when we were doing writes, most of our writes were just going to a small subset of the regions. And the reason for that is that our experiment ID distribution was not very uniform. And therefore, we ended up having some write hotspots. The solution we found that worked really well for us was simply just to reverse the order of the experiment ID bytes, because the lower order bits were much more uniform. Another optimization we did for faster writes is using the deferred log flush. As you all probably know, by default, writes to the write-ahead log are flushed to disks immediately by HBase as soon as they come in. But with the write-ahead log, with the deferred log flush enable, it actually patches them up and can do aggregate writes, so makes it much more efficient to do the writes. Now going on to the reads. As Mustafa already described, our reads are actually much more sparse, but on the other hand, we do have really large experiments. But like some of our experiments span multiple millions of rows, and scanning over them can take a long time if you just do that sequentially. So what we did was simply, our first approach was to simply parallelize our coprocessor execution. What that means is that if an experiment spans from this row key to this row key, you fire off, let's say, maybe 8 coprocessors and split this row key range into 8 ranges. And we found that there was roughly 30% speed up using this approach. But the real bottleneck with this approach is that all the data for a single experiment still pretty much just resides on one region server. And therefore, we hit the bottleneck of just getting data from that one disk. And therefore, ideally, we want to scale horizontally for bigger experiments, so that if you have bigger experiments, you should just be able to add more machines to it and scale with the same latencies. To be able to do that, what we did was to add a user ID, a component of the user ID as a prefix of our row key, as you can see here. And what this does is it splits the data for any single experiment into 16 different areas of your whole row key range. And most of the times you'll end up with those on different regions, and you make multiple coprocessor calls for each of these shards, you can call them. And this really allows us to scale to bigger experiments just by adding more region servers. So a few other read optimizations that we did. Skipping unused columns, like the way we have our queries, we can always figure out a large chunk of our columns which we don't even need to read. So you can use column prefix filters for that. And in most of the cases for our queries, we don't care about older versions of columns. In some queries we do, and that's why we have that data. But for most of our queries we don't, so not reading those. And we have also have a separate layer of caching outside HBase to just reduce the amount of queries that actually hit HBase.
Question?
Yeah.
As you're bringing up the versions of columns that you only get the latest, how did you organize the tables? How many old versions do you keep? Do you go with default of 3, or did you tweak those settings somehow?
It's actually...
Question, please.
So the question is, did we use the default setting of 3 for a number of versions, or did we tweak that setting somehow? And I think we're using just all versions.
Yeah, I think we picked like 60,000 or something.
60,000?
Yes.
Right. Like ideally, we wouldn't really want to lose any of these versions, because for some of these queries, we do need those versions.
Yeah.
But could you help me understand what is the reason to keep so many versions? Because it just seems like most of these versions just duplicate the keys. Am I wrong?
Yeah. So ideally, we wouldn't want to do this. Another thing that we let our customers do, maybe we shouldn't, is zoom into experiments, like modify the time range. And when you think unique counting, to be able to get like a correct unique count, now you need a different point in time in which you start considering people for an experiment. So if we didn't have multiple versions for everything that the user has done, then we wouldn't know, like if we sort of move the time, begin time like further, if we should like now include that user, right? So unfortunately, to be able to like zoom into experiments and get correct unique counts with multiple ranges, we need essentially all versions.
So you don't have a limit of versions. It's pretty much infinite. Is that
Yeah,
right?
essentially.
Okay.
Essentially. I mean, like, we picked a really high number. I think it's 60,000 or something. Yeah.
So now I'm going to talk a bit about how we did our performance benchmarking. When you have multiple approaches you're trying out, how do you figure out which approach to take if you have, and the best way to check that is to just try these approaches out and look at the numbers, and that's what we did. So we have an isolated staging cluster where we ran all of our performance tests. We have a set of synthetic read load which we can use on this, and even though it's a synthetic read load, it's on actual data, so it's pretty representative of actual production traffic. And then we can actually measure the performance across the experiment sizes that we have. And to show you an example of that, when we did our parallel coprocessors, we actually found that for smaller experiments, just to show you, this is on the x-axis we have experiment size percentile, so that's 0 to 100 percentile. And on the y-axis we have what kind of speed up we got for those experiments. And as you can see, for smaller experiments, doing parallel coprocessors was actually worse by up to 40%. But we found that we really cared more about the bigger experiments, and for those we were getting a speed up of roughly 30% on average. And similarly for the sharded versus uncharted schema, you can see here that we actually got a speed up of up to like 8x on our biggest experiments. So to conclude, for fast writes, you should always try to do batch births and evenly distribute your row keys. Use the deferred log flushes if you really have a big write load. For fast reads, make sure you're using coprocessors to aggregate data rather than getting all your data to your client. And distribute your reads over multiple servers. And always measure early and measure often. So we've pretty much finished building this system, and what's next for us is pre-computing results for really exceptionally large experiments, which we can't expect to solve, which we can't expect to respond to with a scan in real time. And other than that, we're looking to take advantages of our schema to create many more features for our product, including complex board types, which involve taking two rows and using that in some way, and other features like session learning. So that's about it for us. If you have any questions?
So in a performance chart, there's a lot of variation talking about speed up versus experiment size.
Right.
So it's extremely jagged.
Right.
So how do you explain that? What does that mean?
So actually, in these charts, I would probably put it to we didn't have a big enough sample of actually experiments that we were querying. But
how many experiments did you perform there?
I don't remember the exact number, but I know it wasn't very large.
Maybe 20 or 30.
Yeah.
We queried these multiple times.
Yeah. So yeah, 30 experiments maybe. Yeah. We queried them multiple times, but.
So 30 of the 30?
30, 3, yeah.
So
Something in that range.
Yeah, but then if you go back to the chart, you see the jagged nature of it. I mean, I would expect some amount of.
So it's like 3 data points on each point, so it's kind of.
3 data points on each?
If it's 30, I don't even remember the exact number, but it's pretty low. Yeah.
How's the cluster installed? Like, is it in
Sorry, can't hear you.
How's the cluster installed? Like the HBase cluster?
Oh, okay. The question is, how is the cluster installed? We're actually using Cloudera Manager.
On EC2.
On-prem or EC2?
Yeah, on EC2.
How many nodes do we have in the cluster?
How many nodes do we have in the cluster? Right now we have 16 nodes in our production cluster, but we haven't transferred all our production traffic to it yet.
what's the Java heap size we use for this?
Java, what's the Java heap size we use?
Yeah.
45 gigabytes? 25.
Yeah.
Okay.
Yeah.
You're writing it through HBase or
Sorry?
You're writing HBase?
The HBase are in HDFS, yes.
So HDFS and HBase nodes are running on the same node? Or
Yeah, on the same node.
How you are distributing the between your HDFS node and the HBase node?
Yeah, pretty even.
I'm not sure I understand the question.
You're running two different processes, right?
Right.
So how you are utilizing the machine?
Oh, the heap. I think we keep it pretty even.
I think so.
Yeah.
Yeah, I'm not positive. We haven't.
Yeah, I don't think we've tweaked that much.
Yeah, we haven't tuned HDFS itself much, which would be an interesting thing to do. But there have been so many things to tune with HBase itself that it's not much of it.
Cool. Thank you. Thanks.
So next we have Rohit Jain, who's going to give us a talk about Trifodium.
Okay. So today I'm going to talk about Trifodium, to explain that term in a bit. But essentially, we started on this project about a year ago, and we announced it as open source on June 10th, just about a month or so back. So it's an extensive project that we have introduced to the open source community. So we started out, this is actually a 20+ year investment in database technology that has been made by HP over time. Its heritage is like nonstop, if you're familiar with nonstop MTP systems, OLTP, operational type systems. So we have a lot of experience in that, and that's basically what we bring. We have taken that code base and we forked it, and essentially have taken that and put it on top of HBase. It's like almost a 250 million plus investment over that time period. So it's a pretty extensive investment, as you see here. So what you see is it's a transaction SQL. That's really our positioning for this project. It positions it for mostly transactional workloads because it introduces transaction capability on HBase. And it marries that with Hadoop and all the benefits of Hadoop that you guys already are very familiar with. I don't have to tell you about that. It has complete full function ANSI SQL support, and we'll talk about later as to what extent it is, but it's got a fair amount of ANSI SQL support we have put in over these years. It's a distributed asset transaction support, and I'll talk to that a little bit as to what asset transaction support we have put in. As you see, that API that we are working with, and that's essentially what you would use on the client side. But we have a server-side implementation for a completely distributed transaction management support. It's really focused around low latency workloads, read-write workloads, and bringing that into the, so taking the NoSQL type of things, but adding SQL and also transactions to that. It's a standard VC JDBC access to the database. You can come in through JDBC type 2 or type 4 driver. And then of course we also federate the data. So I think the key point here is that we have Trevorian tables, which are a relational abstraction on the top of HBase, and you guys are familiar with that. Phoenix does that, Spice Machine does that, right? So that kind of relational abstraction on the top. But we also can join native HBase tables, because some data is not going to be represented too well in relational tables, and lends itself much better to HBase and semi-structured data. And also, if you have data in key value stores like HDFS, you can actually have Hive tables specified, and we go to the Edge catalog and pick them up. So in a single query, you can actually join Hive tables and HBase tables and Trevorian tables. So depending on whether you want more structure, semi-structure, or completely unstructured, you got essentially federation of all of that. Why did we choose HBase versus like Cassandra or something else? Because essentially HBase has a very large ecosystem, and the investments that a lot of tool vendors and database vendors are putting into the Hadoop ecosystem, it makes a good place for us to invest in this environment as well. So let us go into a little bit of the architecture. This is a high-level architecture, essentially 3-layer architecture. You begin with on the top of the client. You could have an application or a tool that is a JDBC and ODBC tool that can access the SQL engine. The JDBC, there are two types of drivers. There's a T4 driver, which is what we've introduced as in our the beta version. Down the road, we are going to have a T2 driver as well supported, so that if you wanted to use a T2 driver, which is a little bit more efficient in some ways, but in a little bit more limiting in the other ways, like a T4 driver can do connection pooling and those kinds of things. So depending on your, what you want to do, you can use a T2 or a T4 driver. On the SQL side, the SQL engine side, which is where our main IP is, you have a master process. The master process is you have multiple master processes. You have multiple master processes running in each node across the entire cluster, depending on the level of concurrency that you desire. So if you have large amounts of concurrency, you might start many more of those, and we keep them around and reuse them. And so the client connects to one of these master processes. The master process then, spawns a compiler and then passes the query to the compiler. The compiler parses it, optimizes it, etc., and spits out a plan, right? And the plan is then executed. Now, at the same time, we are working on something called workload management services, which we're going to bring into this scheme. What that will do is it'll say, well, the system is running hot, and by the way, this particular query has less priority than the other one, and by the way, this guy is going to do a full table scan. So maybe you want to give somebody else a priority, keep this in a hold queue, and execute this other one, right? So the workload management capability will be brought into this framework, so that this will be managed at this point and decide whether you want to execute the query, hold the query, cancel the query, depending on various rules. So that's coming at a later stage. So when you are executing a query, you might want to parallelize it. It might be a situation where you have very large amounts of data you're processing, and so you want to spread that across multiple processes that can go after each of the HBase regions and access the data in parallel. So at that point, we actually spawn what's called executor server processes. So the executor server process, these processes will bring about the parallelism that's inherent in the database. Along with that, we have distributed transaction management. It's completely distributed. So you'll see a slide on that I'm going to cover later, which provides the the commit and the begin and the commit and the abort and all that facilities and the different isolation code that you can get. Finally, you have the storage engine, and the storage engine is essentially HDFS. You got HBase on the top of that. Trevorian tables are essentially abstractions of that, and I'll talk about what the differences are between a typical HBase table and what a Trevorian table, and so you can get a sense of what we do with it. The HBase, of course, we get access through the HBase APIs. We can go directly against native HBase tables. Currently, we are planning to have update stats on this as well, so that we can do better plan choices when we come to start joining native HBase tables with Trevorian tables, because Trevorian tables will have stats, so you can actually do good plans. And then, of course, we access Hive as well, and for Hive, we do update stats. and we do get a sense of what the cardinalities are, so we can do better, have better plan choices. So those are the storage side, what we support. So a lot of capabilities in the engine. So let's go one step deeper to understand what is the engine and what optimizations are there in the engine. So again, this is a lot of years of effort and work. You have optimized performance and efficiency for firstly OLT optimization. So in typical database engines, people say you can either do query workloads, complex, large query workloads, or you can do OLTP processing. You can't do both. Well, we have been sort of doing that for a while. And the way we have done that is we've got a data flow architecture to accommodate very large data flows coming in where you have complex queries, large data sets. But when you have to do short queries, keyed access, OLTP type transactions, small subset of rows, we essentially optimize that. We don't go through the whole data flow, but we have actually a fast path OLT optimization. So you have a master and it's just accessing a row or a few rows. It just goes directly and does that. And it's pretty quick in and out. Okay. But if you want a parallel, you have a parallel query, you're processing a lot of data, then you might spawn a whole bunch of ESPs, what we call executive server processes, and each of them are essentially running against a specific region or part of a region, and basically accessing the data in parallel. Now, in a lot of situations, you have a join happening between two tables that are not co-located, right? And in that case, you have to sort of broadcast, or you have to repartition the table in order to be co-locating them to be able to facilitate the join. So we do that with multiple ESP layers. So you can have multiple ESP layers to do that. The other reason to have multiple ESP layers is because you can have multiple joins, and so those are facilitated by multiple ESPs. Now, it looks like a lot of processes, right? So we do reuse those processes and are pretty efficient about utilizing the processes that we start up. The other thing is it's a data flow pipeline mechanism, and it's a data flow engine. So you're not landing the data at any point in time, right? The data is continuously flowing through memory and through all these operators in parallel through queues that are built in. And so it's all parallel access, it's all pipeline parallelism. Now, of course, sometimes you have a hash join, and a hash join might get a whole bunch of data, and it has to overflow to disk. So we detect memory pressure, and when there's memory pressure, then we automatically overflow. So until we detect memory pressure, we try to keep everything through memory. So, and typically we have found in the past, at least in our engine and our workloads, 90% or more queries are just went through memory, and then some of them do overflow. Now, besides the execution engine, we're pretty sophisticated on the compiler side as well. We've got query client caching, and it's actually patented technology, because what we do is not only cache based on the text of the query, but we actually have the cardinalities on the literals. So if the cardinality on the literals, it deviates quite a bit, we have a separate plan for it. So essentially, we do a lot more around caching and getting the right plan for that particular query, regardless of the fact that it might match another query in the text of it, right? So the literal, the cardinalities of the literals are taken into account. So it's pretty sophisticated caching mechanism. The optimizer, we believe, is one of the best in the industry. We have gone against other vendors I'm not going to mention, but we used to compete against, and we have bid against them, and in benchmarks, and our optimizer is very, very sophisticated. We leverage what's called equal height histograms. Generally, all the database vendors are supporting equal width histograms. The equal height histograms actually give you a better idea about what the skew is, and we have a technology called Skew Buster that we have actually patented that we can leverage in the future, which automatically takes care of skew, which is a very difficult problem even in MapReduce, as you might very well know. So we have patented technology to take care of that, and that's something that we'll be introducing in the future. Now we push down. So the key part of an optimizer is to figure out how do I push down everything to the lowest possible point so that I'm not getting a lot of messages back and processing things at a higher layer, right? Because you want to reduce the number of messages. So what we do is we are essentially pushing down filtering as much as possible and using that with the HBase, and we also push down pre-aggregation and things of that kind so that you're doing a lot of the work down in HBase. And right now, of course, we have a minimal effort we have done in the first release in the coprocessor, but as we move forward, we are going to do a lot of that push down. It used to be there in our previous storage engine. We're just going to essentially do the same with coprocessors in this engine. So you see that. The other thing we have is something called multi-dimensional access method. Again, a patented technology which allows you to kind of skip and jump through a table and access. So for instance, you might have a key, multi-column key, and your leftmost column you don't have a predicate on it, right? I mean, typically you would end up scanning the whole table. Well, we have this multi-dimensional access method which actually positions and skips and jumps and actually can get just the rows that you need rather than scanning the entire table. So it's a pretty cool technology that we have that allows you to do that. In fact, we just got granted a patent a few months ago. This was, put in for years and years ago. So then we of course support secondary indexes. So that's, and then we provide service persistence through Zookeeper. So these processes that are running, they are kept alive through Zookeeper. We also have something called automatic query resubmission. So if we have an error, some sort of a disk error or something like that happens, we automatically, depending on the error code, we resubmit the query on your behalf, on the behalf of the application, whenever it's feasible. Okay, so what's the difference between an HBase table and a Trevorian table, right? So I did mention what Trevorian was. So Trevorian is a Welsh word for transactions, by the way. We really went deep looking for something to name our product, and that's what we came up with. Anyway, so what's the difference between a Trevorian table and an HBase? So firstly, of course, it provides you a relational table. You create a table just like any other. I mean, you're familiar with that with Phoenix and so forth. The physical layout is that we use a single column family at the current time. For space saving, since you've already got the metadata column name defined in the metadata, we just encode it in the table, so you're saving space on it a little bit. And then the column values are, you can define what kind of data type you want. We support various data types I'm going to cover in a bit. And we actually store that in the encoded form. So if you have a table with 5 columns, you get 5 rows if you insert values in each one in HBase, right? Column value combinations with the key and of course the various data types. We have asset guarantees, transactional support, and we use SQL, and internally, of course, we use the API, HBase API to communicate to HBase. So when you have a primary key, which is made up of multiple columns, we create a composite key, and that becomes your HBase key, right? The other thing is that we do support salting. So if you define salting, say using salting, what we do is we automatically do a hash and create a key hash so that the data is automatically spread. You tell us how many regions or partitions you want to set up, and we automatically hash it across that. So that essentially balances the insert workload, and also on the select side, it balances it pretty well on hashing. So that's something that we do, and of course, because the hash key we create is got low cardinality, we can use MDAM now to actually use your predicates that are going against the actual primary key and position it well and not scan the entire table. So that's how we skip a salting key and do that. So we have secondary indexes on an arbitrary set of columns that you can specify. And now coming to some of the DDL, DML kind of support. So we are full ANSI core SQL 99 compliant. And of course we support a lot of stuff beyond SQL 99, like the packages. You probably are familiar with stored procedure packages and some of the triggers and so forth and so on. So we support a lot of capability which is beyond SQL 99 core, and we also support some syntax which is in 2003. We have our own extensions for Trevorian, and we basically things that over the years customers have wanted, we have added. So we have full DDL support, create, drop, alter statements for tables, views, indexes, columns, constraints rather, and then comprehensive support for numeric character, varchar, date, time, and interval, right? And certainly we would love to have the HBase community to leverage the data types, and if not, if the HBase community comes up with data types, we'll of course adopt them, so that eventually the difference between Taborian table and HBase table is minimal to none. That's our essentially the goal. And then we have Unicode support as well. We support various for internationalization. And then we have DML support. So we support insert, update, delete, of course. But we also support the merge command and upsert, which a lot of other databases support. And then, of course, all the syntax that you're commonly familiar with for joins and unions and so on, sampling as well. We also deal with correlated and nested subqueries. So we actually optimize them and flatten them out a lot of times. And we also essentially have normalization that takes care of them, so they're pretty efficiently handled in the database engine. And we have extensive support. We have cursor support as well, fetch support, and so forth. And we have extensive support for functions like aggregate, your aggregate functions, mathematical date and time functions, overlap functions, things of that kind. And also functions that were supported by other databases like Oracle and Teradata. There are very common functions that are used by a lot of other database vendors. We support that as well. So the utilities we support are update stats. We have a pretty nice visual query plan, so you can see the explain plan for the queries. We have control query shapes, so if you don't like the plan or that the optimizer comes up with, well, you can actually influence that. And we have the command line interface, not just OEPC, JVC, the command line interface as well to interact with the system. And then we have full transaction control, begin work, commit work, rollback, that kind of stuff, set transaction. And things we are working on right now, works in progress. A lot of this you will see in our next release. But again, we have no guarantees. But this is what we're working on. The main focus right now is to get the product stable. It's the first release after all. So we're trying to get it stable. We're trying to get it performant. Our goal for performance is that we should have minimal to no overhead on top of HBase, right? We should perform as fast as HBase can. And from a transactional perspective, our goal is, I keep saying 10, 20%. Our development team says 20 to 30%, but somewhere around there. And we hope that as we move forward, our transaction overhead will be less and less. It also depends really, as Gary was saying, it depends on your workload, right? I mean, it depends on your workload what your overhead is going to be for a transaction. What you're going to see is triggers, referential integrity. You're going to get C++ UDFs, which we will look at other language UDFs in the future. Java stored procedures, a bulk loader, transaction recovery when you have a node or a system failure, and rank revoke. So these are all work in progress, and you'll see, much of this stuff coming out. So this is the transaction manager implementation we have, just to show you that it's a very scalable architecture, it's a very distributed architecture. There is no resource contention. There is no one single point of contention here. So we have created a distributed transaction manager which can scale. So what we did was there was a project called HBase TRX that some of you might be familiar with, that used to be in HBase and it was taken out and put aside. It supported local region transactions. We had infrastructure that we had implemented in our database. We provided full XA support for distributed transactional support. So we married the two together, and that's what our implementation is. So you can have multiple SQL processes for any node, and they can participate and create and start multiple transactions. They can participate in the same transaction, potentially. So for instance, when you start a huge insert and you're distributing it through the ESPs, each of the ESPs that are running can participate in the same transaction as the master. So you can all, essentially participate in the same transaction. You have the resource manager library. This is the this does the get, put, delete, get scan or the scanner. essentially implementations, but they are the transactional implementations of those. And those go against the HBase TRX region server. And the region server can actually be managing multiple regions. And you could have multiple region servers per node. Generally speaking, you have one, but most of the time, you could have multiple. On the transaction manager library, that's the one that invokes does the begin, the commit, the abort, and rollback, those kinds of things. And the transaction manager is the one that essentially coordinates that across the entire cluster. So it's the one that manages. There's one transaction manager per node, and then it coordinates with the other transaction managers that are running across the cluster, and essentially works with the region servers across the cluster. So the initiating transaction, whatever node initiates it, that's the transaction manager it talks to, and from then on, that transaction manager manages that particular transaction, regardless of which other region starts participating in that transaction. We have optimizations such as if you have a one region transaction, we don't go to the multiple phase commit. We don't go to we essentially optimize that. And so there are a lot of capabilities in this infrastructure already, and we are going to be enhancing that even in the future. So initially we have read committed support. We are working on repeatable read, which you'll see soon. And then of course, snapshot isolation and things like that. So it's a phased process, but we're going to be getting there pretty quickly. So see for yourself. You try it out. Go to www.travodian.org and download the product. Check it out. We have you will see that we have various teams there. About 50 developers are associated with those teams. And not all 50 are working on Travodian all the time, but a good chunk of them are. The rest, the folks that are, of course, supporting our internal implementations as well. So, but anyway, try it out and join us and become one of the committer and start helping us build this and move this forward. I think you'll find it's a pretty cool technology. Any questions?
You mentioned supporting correlated subqueries, and you also have federated relations. So, I, for example, does not support correlated subqueries. Would you have examples, and you might be able to post possibly in the future, shows using those correlated subqueries?
Yeah, absolutely. Because the correlated subquery is done at the engine level, right? So the scan is the node that that we can have different scans happening. So the scans are feeding into the join, and so forth. So if you have a correlated subquery, we actually do that in the engine.
Could you repeat questions, please?
Sorry, yeah. The question was whether we handle correlated subqueries that are running on Hive as well, because Hive currently doesn't support that. Yes, we will do that.
So for the SQL support, right, do you support the hierarchical query like recursive with class?
What was that again?
Do you support recursive with class?
Yeah, we don't support, the question was, do we support recursive with clause, and we currently do not support recursive with clause.
Another question. So you mentioned that this has support for secondary indexing, right? How does that compare to Apache Phoenix or Kafka performance-wise?
So performance-wise, the secondary index maintenance, just maintenance of creation, or the impact of secondary indexes on your inserts?
Maintenance and the impact on inserts.
Yeah, no, we have not directly measured that. That's something that so the performance side, we haven't really exposed any numbers so far, because I think, as you saw, we are really focusing on getting a performance to something that we want to share with the community. But so far, we have just been running debit credit benchmark, because that was something that we started with, and then we would like to do auto entry, and those are the TPC type benchmarks. So we haven't particularly looked at testing what the overhead of perhaps index maintenance is and so on. But that's something we normally do for our database, so we will definitely be doing.
Two questions. Since you mentioned about auto entry, why do you want
managing already on the code? What are the things that you're planning already on the code? Second question is, what is the origins of the coding HBase? So the first question was, what was the order entry? What are the types of things you want to do with order entry on the coding? The order entry benchmark, you mean? Yeah, I mean, this is really just a benchmark to assess the the TPS rates, right? I mean, eventually we want to be able to establish what your transaction. I mean, everybody asks what's your TPS rate because it's an OLTP platform, right? And the benchmarks usually they like us to look at a TPCC. So we started with TPCA and started easy, and work up to TPCC. So that's what we are going to be moving to TPCC eventually. I mean, it's not TPCC, but a version of TPCC already mentioned. So they're really to assess where we stand and how it relates to like relational databases that have been around and doing this for quite a while. I mean, I don't think HBase is there as yet from a performance standpoint, but we believe that obviously we are riding that horse, so we believe that it's going to get there. And so it's a way for us to assess, how we are progressing to that goal. Second question is the origins. The origins. Okay. So the origins are, like I said, nonstop. I don't know if you've heard of nonstop SQL. We were one of the first OLTP MPP databases anywhere on tandem computers. And we used to beat TPCC. I mean, we did TPC benchmarks and beat everybody at that for quite a while. Then we had Nonstop SQL, which was pretty much an OLTP engine. Then we actually rewrote the engine to come up with Nonstop SQL MX. And the MX was for massive parallelism, and that's where we introduced the whole data flow architecture, and so that it would work with large complex queries. We actually started that on an NT platform because at that point Microsoft had invested $40 million for us to run this database on their NT servers. You remember Windows NT? And then we did this. We called it the top 10 or big 10 top 10 benchmark. What was that?
10 ton.
10 ton benchmark. And that really attracted a lot of attention, and we got bought by, and we think that we got bought by Compaq because of that reason. But Compaq was very much in bed with Oracle, and they didn't want to upset the cart. And so they essentially said, well, we're not going to do this SQL MX thing on NT. So we took that code, put it back on our nonstop servers, and so we ran the code base. So now what you see, Nonstop SQL MX, still running on Nonstop servers, is the code base that came from it. When we forked out of it right around 2007, and we made a run at the appliance business for a while. And you might have heard the database called NeoView. And so we were in the market for a while with NeoView, and that was up to 2011. And we did very well technically and had a lot of happy customers, but we didn't deliver on the ROI. So at that point in time, we essentially were taken internal into the data. HBIT has a massive EDW, 250 terabyte database running three different instances of it. And so they brought us back into IT. And we actually then took this database and now put it on Linux. So that's sort of the heritage of all the database capabilities that it has over time. And that's why you see the parallelism, the parallel engine, and all those capabilities which are generally not needed for operational databases as much. I mean, certainly ODSs need them, but maybe not as much as that. So that's sort of our heritage of where it all comes from. But our focus is really been much more on the transactional side for this particular product.
You have it's a very rich code base, but mainly C++. Those of us who are Scala Java, how would we contribute or take advantage of this?
Yeah, that certainly is a challenge. I mean, we have certain parts of the Java, what our transaction management, infrastructure is something that we would love to sort of move to Java as well. We are also looking at the coprocessor work. So when you're pushing stuff to the coprocessor, that's all in Java. So there are certainly opportunities to contribute on the Java side. But yeah, our base engine runs C++. I don't know if any of the developers have anything to add. There might be opportunities for Java.
What was the most difficult thing getting the code base to run on top of HBase?
Well, I guess the developers will probably answer this much better than I would. But really, we didn't have a whole lot of challenge because we had a scan node, right? And the scan node used to go after our storage engine directly. Now, what we have is you saw the executor piece, and we had what's called the EID, executor in what we call the disk process. And so we have pushed in a lot of aggregation and those capabilities into the disk process. So with HBase, it was easy to just, in fact, with Hive, we just plug in Hive, make that a scan node, put HBase, we can put Cassandra, we can put MongoDB, and we could put anything there as the scan node. It's not that hard, right? I think the challenge is now to take the things that we used to do in the disk process, right, and push that down. So the coprocessor work we have to do in order to do pre-aggregations, push pre-aggregations down, put selections down. That's the effort now that we have to put in. I don't know if any of the developers have any comments on what else was challenging.
How do you support update?
Okay, so currently we are not supporting the versioning in HBase. So, this is something we can do in the future. So we just update the row that you have the existing row.
That's understanding that the HBase by itself doesn't directly support updates.
So the question is, how do we support updates? Because HBase doesn't support updates. As far as I know. Anup, you have an answer? You just update the row, that's right? You just create a new version of the row.
The way we do updates is that you go to SQL semantics, the row already exists, you can update it. If it doesn't exist, it will be. So it's we do is that we check whether that row exists or not. We check input, if there's input.
Any other questions?
Could you talk about the difference between coding and splash machine?
Yeah, so I really don't know much about Splice Machine because they are closed and proprietary. And it's usually pretty embarrassing for us to go and ask them. There's a lady here who's from Splice Machine. She could probably let you know a lot more detail. And she knows our database as well, so she could probably give you a much better view on the differences.
Essentially, these two are doing the same thing.
Well, but we have 20 plus years of investment in this. This is a lot of stuff, and it's not just the syntax, like I said. It's the engine. It takes a lot to build an elaborate database engine. Having an optimizer. We support all kinds of joins, right? I said we support merge joins, we support nested joins, nested cache joins, hybrid joins, hybrid hash joins. We sort of, and that all takes a lot of time and effort. And a sophisticated optimizer to build that uses stats to make hard decisions about this. It's not an easy job. This doesn't. And if you started doing this like 2-3 years ago or whatever, it just takes a lot of time and effort.
It's kept some of us employed for many years.
That's right. And we've been together for many years because we love the tandem culture that still exists within our group. So. Yes, so I think that we're going to base a support model on when we have customers that are interested in getting a support model. Yeah, we can put essentially support. We are looking at that. We are looking at targeting something like that perhaps at the end of the year or the beginning of next year to provide a support version. So that would be the enterprise version, essentially providing support services.
So I'm curious about your performance expectations and projections. Do you expect this engine, when it's ready for general use, do you expect it to be comparable in performance to Oracle RAC, for instance, or to some other
So the question is whether we think that when we are ready to release it by the end of the year, whether it will be ready to compete against Oracle RAC and some other. I mean, I don't think so, right? I mean, essentially, if you look at where HBase is, we essentially can run only as fast as HBase can. And if you've done any benchmarking around even with HBase versus relational databases, there is a fair amount of delta there. I mean, over time, that delta is going to change. So I think the value proposition is going to have to be, what is it you're looking for? If it's, are you okay with paying the huge licensing fee? So you have to look at price performance for one thing, because price performance picture is a lot better than just a performance picture necessarily. The other thing is you want to look at whether you want to capture the data directly into Hadoop rather than capturing it in Oracle or SQL Server or even MySQL and then having to move it into Hadoop, right? So we are capturing it directly into Hadoop. We are removing all latency between the time you capture it and it becomes available for you to access it for reporting or analytics. So you can now use the entire Hadoop ecosystem to go after the data you're capturing. So the value is whether you're bringing in structured, semi-structured, unstructured data all together in one place, you're capturing it directly into the Hadoop ecosystem and removing latency, or what's important to the application. So I think initially you'll see that over time. I believe that we will be contributing to HBase as well. So right now we're busy just getting all the functionality from our database moved into Clavodian. But as we move forward, we have opportunities we've already seen. We used to do something called mixed workloads. So you have short-running queries and long-running queries. What happens is the long-running queries just completely hog the system, and the short-running queries just don't get any chance to work. And that's a big problem. We have solved this problem before, and we know how to solve the problem. We want to bring that to HBase and process technology. So we believe that once we have done the initial investment here, we will start focusing on HBase performance, HBase capabilities, and start bringing that so that the gap that you're mentioning, is.
I didn't mention any.
No, it's but that I'm mentioning that there is a gap. We will try to shrink the gap over. Yeah. But yeah.
If the slides are available on the website.
Yeah, we're going to make that available. Oh, on this website, we will have to see. We'll put it on the wiki. So do you see yourself using MapReduce underneath to run the joins, or will you always run them in your nodes and still? No, we got something much more sophisticated than MapReduce.
So how's your transaction support? Do you use snapshot isolation?
No, we don't have snapshot isolation today. We have just read committed. We'll be providing repeatable reads. So the way it works is that we, and this is really based on HBase TRX. We actually distribute the transaction. So we generate a transaction ID. We don't rely on HBase TRX to generate the transaction ID because we want that transaction ID to be global, right? And that transaction ID then gets passed back to the application. So every put and get that's done, regardless of what region it's done in, inherits that transaction ID, and it uses and caches that in the region server. Okay. So and then there's a prepare phase. So everybody says, okay, are you ready? Are you prepared? You prepare, and in the prepare phase, it goes and asks all the regions participating whether they are ready to commit. At that point in time, this cache of all the updates is written into a log. So it's called it's a write-ahead log, but it's actually right now different from the HBase write-ahead log. But we have plans to sort of merge it with it's called the TH log, and we're going to merge it with the H log eventually, pretty soon. So then what happens is then if you abort the transaction, it can go ahead and essentially, forget the transaction, remove it. Otherwise, it'll go ahead and commit the transaction. And when you commit the transaction, it takes this information from the cache and it then writes it to HBase. So now what happens is if you have two transactions that are sort of conflicting, it detects that at the prepare time, not at the commit time. Actually, at prepare time, it'll identify conflicts, and it'll say, oh, wait a second, I've got a conflict with this other transaction, and it'll abort the transaction at that point in the prepare time. So so that if we resolve the conflict at that time and won't commit the transaction. So you'll never see the records because they were all in cache, but if there's a conflict, it'll abort. Did I answer the question?
Is there any centralized role to detect the conflict?
No, because if you think about it, each region. Oh, sorry. Is there a central place which you resolve the conflicts? The conflicts are happening within the region, right? Each region is managing its own set of keys for HBase, right? In the region. So if any conflict is happening, they know at that region level. And so you detect it there. So it's completely distributed. We don't have any single process, single node, single memory, no issues there. It's all purely scalable. So each region then can detect that conflict and do the abort. And then it aborts abort, and then the main transaction manager that initiated that particular transaction will say, okay, well then I'm going to have to abort this transaction all across the cluster.
Is this essentially a two-phase commit?
Yeah, it's a two-phase commit, right? Yeah.
So did non-stop SQL also use two-phase commit?
Yes.
So where is related transaction? Is it a centralized transaction?
No, the initiating transaction. No, not the main transaction. So you could have multiple nodes, and depending on where you connected for the query or the transaction, it will start the transaction there. So that becomes the transaction manager for that particular transaction. So it's all distributed.
So are you saying if two transactions write to the same region server, then only one goes?
Only the first one will get in, the second one will abort.
Not at the region level?
Exactly.
Conflicts are detected at the region level.
At the region. Yes, completely. And so the recovery is also done at the region level. So what happens is when there's a failure and the region comes in and it's now has to be integrated into the infrastructure, so each of them comes up and says, okay, what do I have in my write-ahead log? Do I have, things that need to be resolved because I don't know what happened to this transaction after I died. So it goes and we have a T log, which is the transaction manager keeps a log of every transaction and what state it was in, whether it was committed, it was aborted. And so this region comes up and says, I think I need some attention and you need to redrive this transaction for me because I don't know what happened to it. So then the TM, which was the initiating TM, gets a list of it through Zookeeper. So they post it to Zookeeper, so it gets a list of it from Zookeeper, and then it redrives those transactions that were in doubt, and then completes either backs them out or rolls them forward. Right?
What version of HBase currently does this?
So we support. We started development on 0.94, but obviously that's sort of old now. So by the time we release the product, we plan to be on 0.98. And we are also in the process, because what HBase TRX did, HBase TRX extended HBase classes. And from the HBase community, we said, no, this is not going to work. You need to do co-processors. So the other thing that we are doing now is taking this code and actually porting it over to co-processor. Somebody asked, how can they help? That's where they can help, because that's all Java code.
So the latest discussions have brought me 2 more questions.
Sure.
If you will entertain them. So the first question is, do you store the transaction logs in HDFS, or do you store them privately in other storage?
So the logs are HBase tables.
Oh, the logs are HBase tables.
And we have instances where we force things to the log,
right.
And there are instances we have unforced write, meaning that whenever they get in, they get in. If they don't get in, that's fine. But the reason we put them there is for efficiency. So in the recovery time, it's a lot faster if you have certain more information on the transaction, but it's not in the path of the transaction.
Right. So the other question is partly related, obviously, is do you leave a transactionally consistent footprint on HBase? In other words, I run a workload through Trafodion, and at some point I shut down the system, I throw away Trafodion, and I'm left with HBase. Do I see, is what I see in HBase transactionally consistent?
It cannot be, right? Because you might have transactions in flight, and they were not completely flushed out. Right? So as I said, you went to prepare state, and some of these, so there is differences. Each node is doing its own. So you said, okay, go ahead and commit.
Okay.
So I said, a transaction got started, and you said, go ahead and commit. 5 regions are involved. Right? 4 regions were able to commit. Okay, so you got the idea.
Well, I understand what you're saying, but this makes me wonder whether there isn't a fundamental issue here, because one of the fundamental principles for databases and storage is recoverability from media alone. Right?
Yes.
And to whatever consistency state was in effect at the point of shut down the system. Keep in mind, I asked about shutting down the system, I didn't ask about the crash.
Oh, okay. No. So if you shut down the system, it'll flush everything out. And actually what HBase does, HBase TRX does, the H log is set to null. I mean, there's nothing in H log, and there's nothing in TH log at that point in time. So it's just completely consistent.
Okay. So for a clean shutdown,
yes,
we have a transactionally consistent footprint on HBase, and I can continue to process that data without Trafodion.
Without Trafodion.
How about
So if you have a crash, then you have to bring the data to a consistent state. I mean, because you have transactions in flight, so you either have to roll them back or you roll them forward, right?
And that cannot be done at the HBase level.
That cannot be done at the HBase level, but one of the plans that we have is that utility that the recovery utility that we have is purely Java. Okay. So that's something that we can actually externalize as a Java utility. So we wouldn't want you to not use Trafodion, but if you decide not to, then you can certainly use that utility to recover.
Okay. Thank you.
Any other questions? Okay.